Welcome to Networks Professionals.
Welcome everyone to this explainer. I am absolutely thrilled to have you here today. Look, if you've ever wondered how the internet actually works behind the scenes, you are definitely in the right place. Today we're tackling a fascinating core challenge. How do network algorithms dynamically adapt to select the most efficient path for data packets in a web of almost infinite possibilities? Every single time you load a web page or stream a movie, an incredibly complex, high-speed decision is made in literal milliseconds. We're going to decode the invisible rulebooks that make all of this happen, and that is what we call routing metrics.
Here's our roadmap for today. First, the path selection process. Second, cost and bandwidth metrics. Third, delay and hop count. Fourth, the power of composite metrics. And fifth, fine-tuning your network. Let's get right into it. Section 1. The path selection process. How data finds its way.
Okay, let's dive into this. When a packet of data is sitting at point A and desperately needs to get to point B, it usually has dozens, if not hundreds, of possible routes it could take. So how does it know which way to go? Well, that brings us to our core definition, routing metrics. Basically, these are quantitative values that network algorithms use to calculate and select the most efficient path for data packets. Think of protocols as the managers that process these specific attributes. By running the numbers on these metrics, protocols determine path costs. And this is exactly what allows them to dynamically adapt to ever-changing network conditions, bypass congested areas or broken links, and ensure the reliable delivery of your data.
Because at the end of the day, data delivery isn't magic, it's math. It is so absolutely important to remember that routers, they don't have intuition. They rely purely on the mathematical lenses that these metrics provide. By quantifying the state of the network, a router can dynamically view the physical world of cables and servers, calculate the absolute best route, and then just adapt on the fly when conditions change.
Moving to Section 2, Cost and Bandwidth Metrics, the first two tools in the router's toolbox.
First up is cost. Now, cost isn't about money here. Instead, it's an assigned, somewhat arbitrary value configured either by a network administrator or by a protocol itself. It represents the quote-unquote price or the preference of traversing a specific path. In the networking world, the rule is incredibly simple. Lower cumulative values indicate preferred routes. Basically, you want the cheapest route possible.
And the OSPF protocol, which stands for Open Shortest Path First, brilliantly illustrates how this cost is applied in the real world. OSPF calculates path costs based on link bandwidth, so what it does is assign faster interfaces a lower cost. By making the faster route cheaper to take, it mathematically forces routers to prefer those higher quality paths. It's just a genius way to manipulate the math in favor of performance.
But since OSPF relies on bandwidth, we really need to clearly define exactly what that is. Bandwidth is the maximum physical transmission capacity or speed of a network link. Think of it as the sheer size of the pipe that your data is traveling through.
You'll commonly see this measured in increments, like 10 megabits per second, 1 gigabit, or even massive 10 gigabit per second links. The crucial point here is that routers inherently prefer links with higher bandwidth. Why? Well, because sending data down a 10 gigabit pipe instead of a 10 megabit pipe maximizes throughput and prevents data traffic bottlenecks. Imagine trying to squeeze a fire hose of water through a tiny garden hose. Routers avoid that at all costs to significantly speed up your overall data transfers.
All right, Section 3, Delay and Hop Count, factoring in time and distance. Raw speed isn't everything, right? Time and network structure matter just as much.
Let's actually slow down for a second and map out the sequential journey of a packet. Delay is the total time required for a data packet to travel from the source to the destination, and it's a compounding issue. First, you have propagation delay, which is the physical time it takes the signal to literally travel over the wire. Then, step 2 is queuing delay. That's the time a packet spends just waiting around in a router's buffer if the network is busy. Finally, step 3 is processing delay, which is the time the router actually takes to examine the packet and figure out where to send it. Every single millisecond adds up to the total end-to-end delay.
Keeping this total end-to-end delay low is absolutely critical. While a slight delay might not really matter if you're just, downloading an email, routers must prefer paths with the lowest end-to-end delay to guarantee fast, real-time data transmission. This is incredibly vital for VoIP, voice over IP phone calls, and video streaming. I mean, if you've ever been on a video call where the audio awkwardly lags behind the video, you have experienced the pain of high network delay firsthand.
Which brings us to our next metric, hop count. This is, without a doubt, the absolute simplest metric in the entire toolbox. Hop count is simply the number of intermediate network devices, like routers, that a packet must pass through to reach its destination. It's used primarily by distance vector protocols. RIP, the Routing Information Protocol, is probably the most famous example of this.
So let's compare two routes to see how this works. Say route A has 2 hops, and route B has 5 hops. To a protocol like RIP, a path with 2 hops is definitively considered better than a path with 5 hops. But here's the fatal flaw of this metric. Hop count entirely ignores link speed. Route A might be just 2 hops, sure, but it could be across incredibly slow, congested, outdated links. Route B might take 5 hops, but utilize blazing fast 10 gigabit fiber optics. Relying purely on hop count can disastrously favor a shorter but much slower connection. It's literally like choosing a 1-mile dirt road full of potholes over a 3-mile, 10-lane superhighway. Doesn't make a whole lot of sense, does it?
Section 4. The power of composite metrics, combining lenses for optimal decisions.
To make the most optimal forwarding decision, we really have to look beyond a single value. Advanced protocols recognize that relying on just hop count or just bandwidth can lead to some pretty poor routing choices. So what do? They combine multiple metrics to get a truly holistic view of the network's health and capabilities.
Now, what's really interesting about how these protocols break down is the contrast in their approaches. When you look at the associated protocols, you can see OSPF focusing on cost based on bandwidth and RIP relying purely on hop count. But look at EIGRP. EIGRP uses both bandwidth and delay as composite metric formulas. By factoring in both the maximum transmission speed and the total travel time, EIGRP creates a highly sophisticated composite score to find the truly optimal path. It basically gives you the best of both worlds.
Section 5. Fine-tuning your network. Applying the metrics to your goals. If you want to optimize your specific network setup, you're going to need a basic checklist. First off, you have to identify the routing protocol you're currently using. Are you running OSPF, EIGRP, or maybe legacy RIP? You obviously can't adjust the math if you don't even know which formula your network is running. Second, you need to firmly define your primary network goal. Fine-tuning your routing configurations depends entirely on the specific outcome you actually desire.
Which leaves us with this final, crucial question to ask yourself. What is your primary goal? Are you optimizing for the lowest latency, meaning you absolutely need lightning-fast, real-time data for things like VoIP and streaming? Or are you optimizing for the highest throughput, prioritizing massive bandwidth pipes for giant file transfers? You have to pinpoint your ultimate network goal before you can correctly adjust your routing metrics. Well, I hope this explainer has decoded the invisible rulebooks of your network and left you eager to dive into your own router configurations to see exactly what math is running behind the scenes. Keep exploring, keep learning, and I'll see you in the next one.
Thanks for watching.